So our next speaker is Brian Woodrich. Brian is another U.S. Fish and Wildlife Service biologist. He currently isn't doing spotted owl work, though. He's doing conservation work for golden eagles, actually, in the western United States. But he's been doing stuff with things with feathers for a really long time. He's going to help us understand better some of the modeling efforts that went into why they drew the lines where they did for the critical habitat unit. So help me welcome Brian Woodrich.
Is this on? Yeah. I'll get all geared up here. Well, thank you for that introduction. This is a really great gathering. It's about time we did this. And what I like about this is it's so inclusive. There's a lot of diversity in the group. There's Californians. I don't know how many, but I'm one. So I appreciate being able to come up here and discuss spotted owls because they're down there too. And I have been doing this a long time, as Cheryl pointed out. So I'll put my reading glasses on so I can commence doing it. How many people here like modeling and think it's fun? Oh, I don't believe that. Okay. Well, good, because this is it's a pretty tall order running through what is essentially a couple of years of very intense effort by a bunch of really smart people. I don't really know how I got on that list, but I got to sort of try to direct things. And it's a very complex exercise, so I'm going to be blazing through it. This talk was originally given by Jeff Dunk, who is considerably smarter than me, and way more caffeinated, so I really have a tall order here. And as Jim mentioned, actually using the same slide, for the conservation planning effort that we use for the northern spotted owl, both in the recovery plan and then subsequently to develop critical habitat, we used a 3-part process, which one reviewer of one of our documents called elegant, and I really like that. And this is something that it's not really new. It's a process that's been recommended in the literature, but this is one of the first times it's been used in a large-scale conservation planning effort that I would say really mattered. I mean, this got a lot of attention and a lot of review. So the process consists of 3 parts. The first of which was a habitat suitability model, forms the basis for everything that follows. Next was a model conservation prioritization, which basically looks at all that complexity of habitat quality in the landscape and aggregates it and breaks it into pieces that we can work with a little more easily. Using those 2 things, we can think of a bazillion scenarios of habitat, of conditions, current and future conditions, which we then evaluate with a population simulation model. All this stuff I'm going to get into more detail later, obviously. A lot of comparison and feedback, which kind of gets you into this zone of, well, here's the kinds of things we'd like to recommend because we think they'll work, and then the big scary part that follows. So I got to lay out a couple cautions here. I've got roughly a half an hour or so to run through what typically we've given an all-day workshop, sometimes 2 days, depending on how intense the people are who want to get it. So this is the 10,000-foot view, and it also gives you a little background on sort of what happened to me during this process. There's parts of this that I'm on the ragged edge of really understanding, but I do know how to present it. I do know what it meant and what it represented. And it'd be better if one of the survivors of that episode were giving the talk, but that's not the case. So part 1, remember in the 3-part process is habitat suitability modeling. And the objective here, well, obviously was to develop models that predict habitat suitability, but also models that predict habitat suitability to the degree of, rigor that allowed it to form the basis of subsequent modeling. I mean, this is a good representation of spotted owl resources and how spotted owls distribute themselves across the landscape. And the model outputs are, we call them RHS, relative habitat suitability. Everything's relative in models. And relative habitat suitability also can be interpreted as a prediction of the probability of spotted owl presence on the landscape based on habitat suitability. Some people call it occupancy, but occupancy as a word has taken on a whole life of its own in spotted owl and population modeling. Habitat suitability in our case is defined fairly broadly. You know, folks who've been working with spotted owls for a while, it's all about, you know, late successional habitat, you know, spotted owl habitat, and that's important, but we looked at a much broader range of ecological conditions that we know from lots of past research on spotted owls influences where they live and how they survive in the landscape. Forest structure and distribution of forest habitat, species composition of the forest, topography, local climate, and things like that influence the probability of presence. So here's a slide that captures about 20 slides in my other presentation. And this really, I just want to run quickly through sort of the foundations of what went into our modeling. The first is we spent, and a number of assistants and technicians and experts spent a lot of time reviewing the literature, especially the more recent information and data sets on spotted owls. A number of people stepped up, in particular from the demographic study areas, and gave us data sets that they hadn't analyzed yet for our use. I mean, this was a big collaborative effort. We also held formal habitat expert panels with a whole range of people from spotted owl researchers, industry folks, land managers, just really getting a lot of input on what habitat's all about for spotted owls. We broke the range up, I call it partitioning, into modeling regions to better capture more locally specific ecological factors that influence spotted owls. Everyone knows that spotted owls in Washington are doing different things than they are on the Redwood Coast, but it's really rarely been sort of systematically looked at. We got a lot of very high quality spotted owl location data. A lot of it came from the Northwest Forest Plan monitoring folks, but we also got a lot of other data sets from various researchers. We were fortunate that we got to piggyback onto the Northwest Forest Plan monitoring effort, which had just developed a vegetation layer for the whole Pacific Northwest range of the spotted owl called GNN. We tested it, and it worked extremely well at showing us the conditions to a great detail on the ground, and also, as I mentioned before, topographic and climatic variables. That's a bunch of stuff to squish into one model. I mentioned we partitioned the range. We broke it up into 11 modeling regions. Again, you know, this usually takes me a half an hour to talk about. And, you know, there's a question earlier about tan oak and disease factors in tan oak. Well, one of the modeling regions is really, that was the driver that resulted in that modeling region being designated, is that tan oak. Tan oak is one of the richest spotted owl habitats there is. Spotted owl densities in mixed Doug fir tan oak are very high. Tan oak, Doug fir, and then especially at the edge of redwood. It's wood rat land. So tan oak is a great indicator of a different kind of ecological relationship for spotted owls. Boom, that's an area we can model in and have a better model than if we just generalized the whole Klamath region, for example. These slides are going to come out multiple times in different talks. We took a multi-scaled approach. So we started our modeling with fine-scale things that we know. I mean, the relationship between spotted owls and foraging habitat and nesting roosting, pretty pretty well nailed down, especially if you look at it specifically to different modeling regions. But then we also recognize that those features and other things that influence owls, like topography and elevation, need to be pulled into the model because they build on that explanatory power. So as a summary, again, this is step one, just the habitat modeling foundation. Based on an extensive review of literature and data sets, a very large, high-quality data set of spotted owl nesting sites, a little over 4,000 of them. Excellent vegetation layer, seamless layer, something we've never had before, something that crosses private lands, federal lands, state lands, everywhere. Included abiotic. We modeled at the core scale, which is about a 500-acre buffer where lots of research on spotted owls suggests this is really where it's at. Things that influence them here have a much stronger influence than the whole home range, which is also important. But the core area is really a big driver. Things that happen in the core area are a much larger driver for spotted owls. I'm not going to get into a lot of detail here. Again, this is one of these things I just have to gloss over. But this just shows you the model results, the relative degree of influence of variables for two areas that in the past have been modeled together, the Eastern Cascades North and the Western Cascades North. And one thing that's really important about these areas is they're big landscapes with not a lot of good spotted owl habitat. A lot of late successional habitat at the extreme north end of the range, even without barred owls, didn't support spotted owls. It's too cold, too high elevation, too this, too that. It's really about where their prey lives. So things like the amount of nesting habitat, the slope position of the habitat, and here's something interesting on the Eastern Cascades, the percentage of Douglas fir in species composition. Douglas fir on the Eastern Cascades is a good indicator of the kinds of places spotted owls live. So this is what the models were pulling together. So we wind up with sort of this mood map thing. In this case, the darker the green, the better the habitat quality. We went through an extensive model evaluation. I actually, well, especially when I started this process, don't like models very much until someone can demonstrate to me that they work really well. Show me how well they work before I'm going to incorporate it into some other process. The first and sort of no-brainer thing we did is we overlaid our model results with hundreds and hundreds of independent samples of spotted owl breeding sites. Very high correlation, which shows in this slide. And we also did a lot of other evaluation metrics to really, we needed to have confidence moving into the next step. One thing that suggests, this is where it starts kind of getting, oh, how much detail do I want to throw at you guys? This graphic shows the distribution of relative habitat suitability by modeling region. So the first cluster of bars shows at really low quality habitat on the far left, 0 to 0.1. Some modeling regions, the Western Cascades North, for example, are 70% really low quality habitat. Tremendous variability in the amount of high quality habitat and then habitat in different, we call them bins of suitability. Then you look at the redwood zone, very little of the redwood zone is low quality habitat. That's a feature of how spotted owls use the landscape in that area. Redwood forest becomes owl habitat at a very young age, and there's a lot of owls in it. A lot of barred owls too, unfortunately. And then other areas, say the Klamath province, for example, has a much more even distribution. It's a mosaic of all kinds of habitat, and spotted owls seem to do quite well in it. And the model highlights that. So the next step is we've created this relative habitat suitability model, and it's this very fine scaled, 30-meter pixel depiction of habitat quality across the landscape. Well, owls don't use habitat at 30-meter pixels. However they do it, aggregate the landscape around them and figure out, is the amount and distribution of habitat somewhere I want to live. So we needed a process to do that ourselves. And fortunately, recent advances, way too much caffeine, in conservation planning software and computer technology really helped with this. So we used a program called Zonation, which basically just, it blobifies things. It takes really fine, detailed landscapes and shows you the distribution of different proportions of value. You want to see the top 10% of habitat value, it'll show you that on a map. And what it's good at is it optimizes efficiency. It aggregates the most habitat value in the smallest area and gives you a huge range of choices to choose from in terms of how you glob it together. So here's a picture of how that works. On the left is our raw relative habitat suitability. Very nice, easy map to correlate with where owls, we overlaid this with owl home ranges on telemetered birds, and really nice. Almost useless from this larger scale perspective of how do you systematically make that into a series of sort of reserves. And you look on the right, and that's what zonation does. So the top 20% of habitat, for example, is in this sort of plum color, I guess, on this screen. And you can just increase till if you want to see the top 100% of habitat, it's almost the whole landscape. So what we use that process to do is come up with a bunch of scenarios. Here we're calling them networks. They're sort of alternative networks. What if scenarios? What if you used, this says Z30 all, which means zonation, the top 30% of habitat value across all lands, public, private, doesn't matter. Versus Z70 all. And you can see this is supposed to be in acres. Well, I didn't make this slide, so it's okay. Yeah, so Z30 all is only 3 million acres. Z70 all, so the top 70% of habitat value, which is the vast majority of it, but on public lands only, is 10 million acres. And we had, Z 20, 30, 40, 50, 60, 70. So we have all these different scenarios to choose from. And then moving right across this they're called comps. And what these were is a composite of the zonation scenarios, but specific to each modeling region. See, there's just layers of complexity to really mess you up here. So composite 1 might be Z30 in the redwood zone because habitat is so widespread, and it might be Z50 somewhere else because that's what it takes to get any kind of a good network of habitat. So this just kind of gives you a picture of the range of things we compared. So we took all of these different scenarios and went into the population modeling mode, which is by far the most complicated part of this. And Cheryl's been using this analogy of we're backing the truck up, so to kind of go back and, well, this is a part where I'm going to try not to just back the truck right over y'all, and all the hands shoot up because everybody's just kind of going, huh? So for the population modeling, we used HexSim, which is a mouthful. It's a spatially explicit, individual-based population simulation model. Okay. What's great about HexSim is that it incorporates all the stuff that Betsy talked about earlier and a lot more. There was reference to the late Bob Anthony earlier. This was sort of his brain dump. We would work through the data sets and he would tell us if there were missing parts, he and several other spotted owl experts, to really, it's called parameterize HexSim, make it work. It incorporates the demographic parameters, spatial information, information about resources, how big an area do they use, how much forest do they want, all of that can be built into HexSim. And HexSim is created by Nathan Schumacher in EPA here in Corvallis, which was good for everyone on the team who lived in Corvallis and Portland. But as mentioned earlier, what we're comparing in HexSim is relative population metrics. yes, we like to think that we at least got close to what populations might have done in all these scenarios, but it's really relative. So we used HexIM to ask some questions. One, well, what is the relative impact on spotted owl populations if? One, barred owl encounter rates, which is the probability that a spotted owl that is setting up its territory is going to bump into a barred owl. These were all provided to us from empirical results from demographic study areas. What if barred owl encounter rates increase or decrease in the future or over time? What if relative habitat suitability increases or decreases over time? What if critical habitat or some kind of reserve network was designated in a particular way? All those different zonation scenarios that I mentioned earlier. And what HexIM does is it gave us a consistent platform to compare population responses to all these scenarios that we want to compare. And when I say a consistent way, it's repeatable. In fact, both critics and advocates of this process have taken all of these platforms that we used, and they're rerunning them and running them under different scenarios to see how they worked or to see if they can find problems with it. And that is, you know, somebody might say, well, that's maybe not a good thing, but I think it is because it does allow people to, I wouldn't say duplicate what we did, but you can expand on it, you can test different conditions, do different kinds of sensitivity analyses. So here's the part I like. The guy who made this thing goes through it. It's like a squirrel on caffeine. So the HexIM model is it's a series of events, and it's if you know anything about spotted owl ecology, it's very intuitive. But first, we create what's known as a hexagon map. So it's a space-filling map of looks like a beehive, or honeycomb, of hexagons that are about the size of a spotted owl territory. This map covers the whole Pacific Northwest. And we begin with 10,000 owls. So you can imagine we have the Pacific Northwest with no spotted owls in it. I don't know if any of you ever played the game The Sims. Same technology. So you begin with 1,000 owls, and the way I like to do it for general audiences, you fly over the Pacific Northwest and you're flinging out all these owls, and they have little briefcases that tell them what their life's going to be like. And they land and they're like, what do I do? And so they have all these rule sets. And all the rule sets come out of what Betsy was presenting earlier, plus all of the spotted owl research that we could pull together. So we know how they disperse. There's huge amounts of data on how they disperse through landscapes, what kind of habitat they stop in. That's built into HexIM. What size their home ranges are going to be based on habitat quality, that's built into HexIM. We know a lot about their encounter rates with barred owls. And I'll touch on this later because this is something that's changing through time. So we did this modeling at one slice of time. It's already different. So each spotted owl looks at their briefcase and it says, bummer, you've got a barred owl. That influences the rest of its life history. So survival of those owls in the landscape is a function of age, the resources available to them, and barred owls. How many barred owls are in the neighborhood? Reproduction happens. They reproduce in roughly the same way that's observed across the demographic study areas. It depends if you have barred owls. Well, actually, no, not in this case. It has to do with the age class of the spotted owl and the habitat, the territory quality that it landed on. Dispersal occurs, and then the process starts over. So these owls that have been put in the landscape, they've settled the landscape and filled it with 10,000 owls. We know that's not sustainable, so that will start dropping. They reproduce. Those juveniles are now out in the landscape looking for territories, and that's iteratively now HexIM just runs every year. Survival, reproduction, habitat change, barred owl change. Every year the scenario plays out. Now as these scenarios as the Hexim life cycle sort of plays out, we change the world they live in. So we can change barred owl numbers. The probability of barred owl encounter, we've changed that. We can change habitat through time. We run the model for 250 or 350 time steps, which are kind of like years in a model. And we evaluate the outputs. So first thing is so what? Does it work? Is there any reason to believe that, that these outputs resemble anything real? And we wanted to look at that. So the first thing we did is we compared just the pure model-driven number of owls that occupied the demographic study areas, so we could clip out those parts of the landscape. We compared it to the number of spotted owls actually in those landscapes. And without any explanation, for the uncertainty that resides in this kind of modeling, these are very close. In other words, we looked at this and just went, wow, this is great. But you'll notice in a lot of cases, we underestimated the number of spotted owls that were in those areas. Well, as Betsy mentioned, the number of spotted owls in all of those areas was already steeply declining. The modeling looks at the barred owl influence and a lot of other things, and it's giving you this prediction, which is really kind of out ahead of the data from the demographic study areas, because as you saw, they're always a few years behind. So in reality, in most of these areas, we actually over-predicted a little. And that's the whole thing with spotted owl right now. It's a very rapidly changing situation. So that was really nice. We were able to move forward saying, well, at least this seems to work in a reasonable way. Another thing we looked at is we got a lot of dispersal distance information from Eric Forsman from Pacific Northwest Forest Service Research, and we compared it to the dispersal distances of the owls in Hexim. The neat thing about owls in Hexim is we track, the program tracks everything they do. So you can watch dispersal flux, you can watch connectivity, which is the long answer to the question earlier. You can watch sources and sinks as they change through time. And so we looked at the dispersal distances of the owls the fake owls in Hexim, I guess they're simulated owls, and compared that to the empirical values. And again, no, these curves aren't identical, but they're incredibly close for this kind of modeling over huge areas with all the variability. And actually, we got some additional data sets from Eric, and we've actually improved this relationship a little bit, but it's not important to show that. So scenarios, we looked at a lot of different stuff. So we have 3 habitat scenarios. Hab 1, here it says isolated reserves. Really what it means is all habitat outside of reserves loses quality through time to the point where it supports spotted owls, but not breeding spotted owls. And that's not a reasonable thing to think is going to happen out there. Remember, this is for comparing. We want to set high bar and low bar and a couple middle bars to kind of see how the system works. Habitat 2 maintained high quality habitat on public land. So that's in and out of critical habitat or the reserve network as long as it's on public land. And 3 maintained high habitat quality just about everywhere. And these sound really goofy without all the backup information, which is the habitat is never static. What we did in the modeling is we looked at the habitat change through 3 decade time periods at the pixel scale. So when we say we maintained high, we're basically saying habitat kept changing the way it did through time over the last 30 years. But in some areas, it's going to have a steeper downward trajectory. In some areas, it's going to be steeper upward. It's not the cartoonish kind of everything outside of the network goes blank. There's no habitat value. This basically, the landscape looks and changes a lot like it has been. Later in the process, we lumped these into optimistic, which really just kind of the habitat just across the whole landscape kind of moves forward as the way we observed over the last 30 years, versus pessimistic, which is outside of the reserves, the quality does decline. Barred owl scenarios. We ran Hexim with no barred owls, which was very nice, but not very realistic. We ran Hexim with barred owls at their currently estimated encounter probabilities, which, remember, they're going up all the time. So basically, we stopped them in 2011. We kept it at 25%. Uh-oh, I'm in trouble here, she tells me. And we let it go to 50%, which some demographic study areas were already at 50%, but many were lower. And we put a ceiling on it, because if you let barred owls go to 70%, spotted owls just vanish from the landscape, and that's no fun to model. It's kind of depressing. So this slide just basically says we looked at about 108 combinations of all that stuff, barred owls and habitat and different network configurations. I showed this slide before. What that gave us is a lot of different, this one has acres, a lot of different network sizes. And I hate using that metric because it's really all about the network's complexity and where the habitat is, not so much just the gross acres. Okay, metrics, the populations, we looked at the population change through time, spotted owls, just the overall numbers. Pseudo-extinction thresholds, which means they hit some lower level that we weren't very comfortable with. It's called pseudo-extinction. So range-wide, that might be 1,000 females. And the percent of simulations during which the population went extinct, and then the overall population size. I could spend a lot of time on this. I can't. Basically, I should, but I'm standing between you guys and lunch, so I know better than that. What this really showed us is that, it became a barred owl modeling exercise, and there are a lot of folks very interested in taking this to a more sophisticated level, is that when you get about 0.35 barred owl encounter probability, spotted owls start to really get into some trouble. When you hit 0.5, as you notice, 0.5 everywhere it says, the metric in here is basically the percent change in population size over a couple hundred years. So with barred owl encounter rates at 50%, spotted owls drop down to 10 and 13%, the populations of what they are today. So they just really start to tank. The new meta-analysis would suggest that it's happening way faster than our model predicted. Versus with no barred owls, pretty much all of the habitat of the different reserve designs function really well. That says a lot about the relative importance of habitat and barred owls in this thing we have going on right now. There's a lot of habitat out there, but a lot of it's not available to spotted owls. So in general, the results, extinction did not occur range-wide. Just looking at all of those modeling units together, didn't occur range-wide, but some modeling regions, especially under current barred owl encounter probabilities, particularly in the north, did drop to extinction. Pseudo-extinction thresholds were commonly exceeded in some modeling regions, especially in the north. And the Northwest Forest Plan, I don't know, I'm not going to focus on this because it's an unfair comparison. The Northwest Forest Plan was built to do a lot more than conserve spotted owls. It performed poorly because it incorporates a whole lot of habitat that wasn't meant for spotted owls. And it was also based on information in 1993. So summarizing the results, we generated all these different curves for each of these brightly colored curves represents one of the reserve design scenarios. So if you hold barred owls and habitat constant and you just look at how spotted owl populations are influenced by the reserve design, these are the kind of curves that we generated. And what I'm going to do is skip a couple because I'm running out of time. So again, some modeling regions performed poorly in all networks. Owls went to extinction in the Western Cascades North, over 75% of the time. And that appears to be starting to play out now. And 21 to 35% in the Western Cascades Central, another area where owls are quite limited. You go to California, on the other hand, and the inner coast range of California, Klamath Province, east and west, which does come up into Oregon, perform the best. There's a lot of reasons for that, and Tan Oak's part of it. We had 0 extinctions, largest populations at the ends of the simulations. Well, barred owl densities are still quite a bit lower down there. The habitat mosaic, a lot of federal land, habitat mosaic didn't dip anywhere near as far down as it did up in the Washington and Oregon coast ranges. And the point of this slide is really just we have a lot of comparisons across all of these different potential candidate critical habitat reserve designs. And we have all these different population metrics from the spotted owl population simulations to compare. And that's really the heart of how this process worked. Now this goes from Comp 1, it shows 1 through 7, but subsequent to this PowerPoint being built, there were the last rounds of comparisons, which were really part of that feedback loop and then policy and process. Biologists in different agencies and the Fish and Wildlife Service sat down, took a really hard look at these maps, and obviously from a modeling effort like this, there are places that they weren't in critical habitat, and it was obvious there was a cluster of owls and some good habitat. Who knows why it was skipped? Not a lot of that. Areas were carved out that were lower quality habitat. And there's this adjustment based on expert opinion and feedback. Although I will add, it was a very rigorous adjustment. There wasn't just sort of, well, we need to cut it by 25% kind of thing. It really stayed very close to the intent and the outputs that we got from the modeling. And then after we did that, we tested it with HexSim. So it wasn't just well, here's what we think. It was, well, here's another design. This was suggested by a group of biologists. Run it in HexSim. You saw this slide before. This whole 3-part process really gets at this idea of efficiency. It's like get the best habitat, pull it together, and that's habitat through time. It's not just a snapshot. Pull it together in a way that maximizes its utility for spotted owls, and those are the composites that rose to the top. And the ones that maximize spotted owl population size and persistence. Those are the ones that rose to the top and went further and further into the critical habitat designation process. Oh, look, I'm summarizing. So the process we use, 3-part process, synthesized, and this is a real good use of the word synthesized, information from these 3 modeling platforms, gave us a scientifically defensible and a repeatable process for comparing among all these different critical habitat, competing alternative networks. And this, we're trying to do this for golden eagles right now, and we know so much about spotted owls. There's such a huge amount of information available on spotted owls, in particular from the demographic study areas, is that it's hard to think of another species, maybe African elephants, where you can do this kind of a process. So we kind of cheated. We got lucky. And again, the process is very amenable to coming up with alternative sort of what-if scenarios. The state of Washington right now and the BLM in their plan revision are doing exactly that, taking the modeling process and saying, okay, well, here's more things, finer scale changes that we'd like to evaluate and run through the modeling. And as I mentioned earlier, this is a process that provides a sort of a menu, and then there is, as Jim pointed out in his presentation, there is a policy and public process that gets you to the final designated critical habitat. Although, I shouldn't say although, in the case of spotted owl critical habitat, that process led us to basically an output that was very, very similar to the best performing, purely model-driven and expert opinion-driven reserve design. And again, a whole lot of people considerably smarter than me pulled this together. Yeah, it was a couple years of pretty intense effort, so the group deserves a lot of recognition for that, and some of them are here. That's it. I cleverly left it no time for questions.
Brian will be here later for questions as you cogitate them over lunch. So he took us down to 10,000 feet overview, and none of our heads exploded.